This is a video just to show a few examples of how I try and help students see what they're doing with math. The other day we were working in a calculus class and we had a pumping problem. The work required to pump fluid from a hemispherical tank, and I had drawn that on the board and students were kind of trying to draw it as well, and they just weren't getting how to find the connection so they could find the radius of a representative level of the fluid. And we ran out of class time, so I went back to my office and I just built this simple visual. At the first of the next class we went over this and it made all the difference in the world. I first let them see this and then said, so if I made a line here, do I know how long that line is? And they could all see that it was also R. And then I made a representative little piece at some level what the fluid would look like, and then we decided to call this piece Y. And then I asked them what this radius would be at this height, and we called it R sub S. Then they had them study this picture for a minute to say, is there any way we could get at the connection between this height Y and this radius R sub S? And by having this visual, pretty soon a student suggested we draw a line like this, and then I asked them, well, will we have any idea how long that line is? And they could see that that was also the radius of the sphere that this was the upper half of. And then by the Pythagorean theorem, they could make a connection between the Y and the R sub S at any given height then. So the picture made the difference. I love to incorporate any interactive figures, things that helps them visualize. We were talking about linearization. This was a great visual one that I like to use because it's very obvious to students what's happening here. They can see how if we're trying to approximate the circumference of this circle by using a linearization, not only is it showing them how we are doing here, but we're seeing that we approach 2 pi as we have the circle of radius 1. I also like to use just in the PowerPoint the animations there to help them visualize as they're learning about graphing these parabolas and clearly seeing what each piece does to transform the parabola. It's nice to actually show them that. So we see this first that we have this horizontal shift of 3, and then we have a vertical shift down 4, and to let them actually see that happen helps them to remember. And it's so much better to show a student what a tangent to a curve looks like than to try and explain it in words. We actually formalize it later, but to get them that concept of what a tangent is, to actually let them see this makes a big difference in understanding. And this epsilon delta, to let them see what's going on graphically before they try and understand algebraically how the formal definition of a limit works, is very helpful. And just here's an example how we show that we want to be within 2 of the function value here, and so we look at what it would require for our input, our x value, so that we were within 2, and then we could see that we would need to be within 1 of this value 4, and we could see the area where this would work. And then we can generalize and talk about it. Well, what if we were within some arbitrary given epsilon greater than 0, then to be within delta of the x value that we are approaching. And having this visual graphical connection and then formalizing it makes a big difference in student understanding. As we are looking to do the washer method, to actually let them sort of see the rotations, just an animation, a simple one in PowerPoint, but then to ask them, okay, so what is that radius? And they can very clearly see when we rotated around the x-axis that this was the y value there, and then similarly see how this would look different if we rotated around the y-axis, and then also see for a representative slice that our radius would be the x value. Just to share with you here to show them how when we could sum up here these terms in this sequence that was infinite, but how we would get a finite sum here. So here we have this series because we're summing these up, but we look and see that when we do that, here is a good visual to help them see, since we're adding half of what we have left each time, that we do approach a finite value here. Another visual as we're looking at partial sums to show how we could have this infinite sequence, but the partial sums could have a limit on those, and if they did have a limit, that it must be that our it must be that our term would need to go to 0. So the limit then goes to infinity of our nth term. It must be 0 to have this partial sums converge. Nice to show and be able to take advantage of looking at the color to show how we could graph from a rectangular coordinate system to a polar coordinate system and visually show what each piece of that was as I was teaching this on the various intervals and how it would convert to a polar graph. I also like to, when I can, have the words and concepts that we're learning help to visualize. Students have often said that they can picture this in their head later to help them remember the meaning. So an even function, when I do the word even, to clearly show that symmetry, and also an odd function to clearly show that symmetry. A couple other examples as we talk about increasing, decreasing, or constant functions to actually help them visualize that to help remember those terms. Another example is piecewise functions, and to actually show the piecewise functions being built with the various pieces. So looking here and just very clearly showing them, having them take each piece. And so first we're looking at f of x equals negative x, but then considering the domain and making that domain restriction, and then also looking at the other part of this graph and originally just looking at what x squared looks like, but then considering the domain, we only want this greater than or equal to 0, so clearly showing that as well.